Dynamic point fields. Towards efficient and scalable dynamic surface representations. Recent years have been marked by a significant progress in the field of neural 3D scene modeling and reconstruction. Currently, the best-performing methods for surface modeling rely on implicit representations combined with auxiliary data structures, like octrees or hash maps. A number of works have also explored the applicability of implicit models for modeling dynamic surfaces. We begin this work by revisiting point clouds as surface modeling primitives, and demonstrate how surfaces of arbitrary complexity can be efficiently modeled as sets of 3D points with associated features, such as normal directions. Here, we visualize 3 scans represented by our method. We show that while simply storing randomly sampled points from a surface gives suboptimal results, the proposed point optimization scheme leads to an optimal redistribution of points, and improvements both in terms of surface reconstruction quality and visual appearance of point normals. Compared to the state-of-the-art implicit models for 3D surface representation, optimized point cloud model offers better reconstruction qualities on all metrics, while taking zero inference time thanks to its explicit nature. Next, we extend the basic point cloud model to handle dynamic surfaces. Inspired by the latest works on deformation networks, we model surface dynamics with a compact neural net that maps every point and its associated feature in a canonical cloud to a new location. While this formulation is directly applicable in the case of small and smooth deformation, it fails to find a plausible deformation field in the case of rapid and complex motion. To alleviate the problem, we propose 2 techniques for learning plausible deformations. First, our explicit 3D surface formulation allows us to use some classical constraints for learning deformations in 3D space. In this work, we use the as-isometric-as-possible constraint to guide our learning, which enforces the preservation of distances between points in the canonical and deformed space. Please pay attention to the preservation of fingers in the deformed cloud when optimizing with the isometric loss. We can also enforce the same constraint on the intermediate deformations to promote meaningful interpolations. We compare our model to both SDF-based models and state-of-the-art non-rigid point cloud registration techniques on diverse types of surfaces, and show qualitative and quantitative advantages of our model, both in terms of reconstruction and registration quality. Please pay attention to the reconstruction of the tail, paws and ear locations of the presented feline model. We also introduce a guided learning approach. In the case of dynamic humans, we can directly supervise our deformation network with information on the dynamics of the vertices of the underlying minimally clothed human model. The usage of the introduced guidance regime benefits both the SDF baseline and our reconstructions in the case of the challenging recent scans. However, our method provides significantly lower reconstruction errors in the areas where no supervision is available. Please pay attention to the reconstruction of the subject's dress. Finally, we showcase the advantages of our approach for animating 3D humans in challenging clothing. Using the introduced isometric and guidance losses allows us to perform a single scan animation. When a collection of training scans is available, we can use the closest pose as a starting point to drive our animation for an improved realism of cloth wrinkles. Using this technique, we can repose the canonical scan to highly challenging target poses. Here we show the results of our method on the recent dataset. We compare our model to several state-of-the-art techniques. Due to the reliance on linear blend skinning, the baseline methods often struggle with loose garments and skirts. In contrast, our method offers a new paradigm for clothing modeling, which directly optimizes for a smooth deformation field that preserves the continuity of cloth surfaces. The qualitative advantage of our method is also verified by a clear winning margin in the performed user study. Thank you for watching.